Okay, now I have the rather easy task of introducing Near, which is if you are participating in ICAPS and did not accidentally walk into the wrong room, you already know who Near is. So he needs very little introduction. But I do want to say, this space of large language model versus plan and like trying to integrate the two is a very hot and exciting one, but it's usually done mostly by people who do not know what planning is. Neil is among one of the few exceptions who's doing excellent work, where he's starting from a very good foundation of what planning systems should look like and how we can meaningfully integrate them with large language model. So I'm really, really excited to hear what Neil has in store for all of us. Thank you so much.
Thank you. Thank you for the introduction. The title of the talk, I think, portrays what I want to say here. I would like to start first by acknowledging the traditional owners of the ancient land where we actually live and work, which is the Wurundjeri people, and pay my respects to the elders past and present, which is something we generally do when we do traditional events in Melbourne. Okay, now let me pass my slides. Okay, so now a quick introduction about myself. I grew up in Barcelona. I did my PhD with Hector Gebner, and then I came here in a day that is impossible to forget. 12, I landed in Melbourne. It was a beautiful sunny day. Next day, it wasn't. So I learned to find that Melbourne has an interesting weather pattern. In terms of things that interest me, planning, generating tools, algorithms, I might try to maintain and help and contribute to some of the tools that you might be able to use in our community. I've been focusing also on working in the area of week-based planning. Lately, I also got interested in goal and intention recognition, and in general, the integration of planning, learning, and control. And I found that it's quite interesting to actually work on benchmarks that other communities are interested in, because that's a very quick way to show that, well, we have common tools that and components that then we can relate and talk to each other in a language that we understand. And if you want to go surf together, play football, we can talk about it. I don't like Barcelona, but because I like to lose, and I'm a fan of Espanyol, if that's rings the bell. Okay, and then I think it's important to notice that science is not a solo effort. It can only be done with great collaborators, and in this case, I was quite lucky to work with Chao. It's a PhD student, and he's writing his thesis right now. He's on the look for the next adventure. Then I was working with Sukai, who is actually located in Monash. Then with Professor Chris Ehinger, she's from computer vision. And then with Professor Trevor Cohn, who got hired by Google in Sydney recently. So you can see that at least I was lucky that I was talking with people that are not familiar with planning, and we could find common interest still. So just as a way to motivate planning in the world of LLMs. So if you try to use LLMs to plan, you can do something, for example, like put in a classical, well-known problem, which is the river crossing problem. River crossing problem, you have a set of animals and some food, and then you want to cross them with a boat that has capacity with either food or animal and a person. And there are some constraints. You cannot leave the ship alone with the food because the food will get eaten, or the sheep and the wolf alone because the sheep will get eaten. So you have to be careful about how you move animals and food one by one. Now, let's say that this is, too much to ask for an LLM. So let's simplify it. Let's remove food, remove the wolf, you just have the sheep. And you tell, look, you have a boat with capacity of one for one animal, you have capacity for the human. Can you tell me how many trips do I need, and actually the smallest number of trips, to cross from one side to the other one? And I think that any human here in the room would realize that I simplify the problem, right? One trip is enough. So Jan LeCun actually posted kind of like a meme saying, look, I posed actually this problem to Claude, which is quite strong generating code. And the solution that it gave me is as follows. You actually correctly load the ship in the boat, take it to the other side, then you come back to the shore, you put the whole human back on that side of the shore, and then you go back with the human. It clearly suboptimal. And why did it give us the answer? Well, most of the examples of solutions that was trained on had constraints. So if you remove constraints, how can you realize that those constraints no longer apply and that you can get a better plan? So certainly, since that picture until now, a lot of things have happened. It's a fast-moving field. LLMs, right? Language reasoning models are quite popular now. So literally last week, I said, surely ChatGPT can do that. And after thinking, it's a bit small, after thinking for 5 seconds, it gave me the wrong answer. Okay, so then I was a bit frustrated and confused because if it thought for 5 seconds, surely it should do better. So I entered the prompt again in the same context. And now after thinking for 9 seconds, it got it right, which it's even more confusing for a few reasons. One, because I don't know what's the difference of the different patterns of thinking. And that's a bit to say that inside, they do have their own heuristics of how much it thinks and how much it validates each of the steps of thinking. And then I realized that I had typos. So I wrote the in the incorrect way. And at least in my world, what I would like to see is that something like that. You've got the wrong predicate. It doesn't exist in your domain. Please try better than that. So when we try to use formal reasoning, I expect these kind of answers when I introduce errors. Now, Jan LeCun mentioned, you know what, LLMs don't have common sense, they don't have an understanding of the world, and no ability on plan and reason. And I think that message was well portrayed by Kartik, a student of Rao, and many other papers, and Sarath as well, that they cannot plan. And once you have a language reasoning models, they still cannot plan reliably, as I just showed. It might work if you try many times. And so if we want to introduce a bit more reliability, we need to think about how to actually make the language models use formal methods, formal reasoning, which for us is basically using encoding in PDBF, okay, or using the thoughts or the way that in our community we express formal models. Another way to think about it is it's a well-known problem that someone has to come up with. Even if it's a user, if it's the LLM, they face that problem if they are to use our solvers. So in the next slide, I'm going to show a little bit how hard it can be to actually use formal reasoning models. And this actually comes from a paper from Rao's student. And what they tried is they said, look, a simple pipeline is you've got a natural language description of the problem. You try with an LLM, you ask it generate an action schema for us, and then you have a human expert try to validate whether the action schema is correct. And if there is any error, you iterate back. And so let's assume that, well, if you have a missing precondition, missing effect, or a typo, you should get that type of error and you should fix it. So how many times do you need to do that? Right? What they reported is that it's not 10 times, it's actually 59 iterations, which at that point, maybe you start from scratch, right? And you let LLMs do their work in another field. But why is that happening? Well, let's assume that you have M actions, let's say 10 actions in your action schema. Let's assume that your probability of getting a valid action is 0.9. The probability of getting a full action schema correct degrades gracefully because those errors compound. So at the end, let's say your probability of getting an action schema fully correct is 0 to 34. And that's with a very high ability to get a single action correct. And so that explains why you need many iterations. There's a second issue. So that's the first issue. Second issue is the area of alignment of intentionality. And a quick example is, let's say, the user says in natural language, look, I've got a set of books, just sell them quickly. The LLM or the human expert that's trying to create a PDL model might have a different interpretation of what quickly means. Quickly means a day, literally now. Can I sort them by color, by topics, continents? Right, there's plenty of ways to interpret that. And so that alignment or misalignment is also an issue that we need to address. So our proposal is as following. So I'm gonna deconstruct this pipeline in a minute, but we try to address these two problems. So what happens when it's very easy to get wrong models, and what happens when you have misalignment in intentionality. So what we played here is with the following idea. We know that the probability of getting things wrong is quite high, but at least of getting one action schema is also quite high, right? So I'm trying to look for a needle of the hay in the hay. And if you do that interpretation, so let's create as many action schemas as we can, then the likelihood of having at least one correct is quite high, regardless of your accuracy. Now, the issue then is that we have a combinatorial problem of testing a large number of action schemas and checking their validity. And so what we did is, I'm going to stop the filtering now, but let's assume, I'm going to talk about it in the next slide. Let's assume that what we rely on is that we know that in our community we have quick tests, polynomial tests, to test the validity of an action model. So what we did is we said, okay, look, just let's throw it to a delete relaxed planner and see if it can solve it. Okay. First, it quickly detects if there is lexical errors. That's easy to check. And if the grammar is correct, is it solvable? Does it say, look, it's not solvable in the interaction? It's quite easy to prove that. And now, if I get an action schema that is solvable in the interaction, our conjecture is that it's very likely that actually it will have solutions, valid solutions in the real problem. To give you a sense of how many problems we can test action schemas, it's around 50,000 action schemas in 2 minutes. Just calling the delete relaxed planner with 32 threads. Yes, it's quite quick, the number of action schemas. Still, you can imagine that combinatories can kill you quite quickly. So what I'm going to show next is the filter function. So can we actually do better? And before sending everything to the delete relaxed planner, can we filter and make sure that the ones that we send, they have two things. First, it's likely that they're correct, but also that they're semantically aligned. Okay? And for that, I'm going to move into this topic that actually Sukai introduced me to this work of Warren Weaver, which had a seminal work on machine translation before actually AI was invented, right? So what he posed is that if you are to translate a text from Russian to English, is nothing else than text written in English, but with different symbols. Right? It's a coding experiment, but the meaning is the same. So using that metaphor, then we can choose what is Russian for you, but let's assume that the natural language description is in English and Russian is PBBL domain. Well, the task is that it doesn't matter which symbol do you use, the semantic meaning should be the same. Okay, and in our modern world, the way to test semantic meaning is by using sentence encoders that encode different tokens into an embedding, and then you can look for the distance of those embeddings. Okay, so simple way is looking at cosine similarity. So you can test what is the semantic embedding of the natural language description, what is the embedding of the PDL domain, and try to see if they're aligned. So once we can test that alignment, we did something called conformal prediction, which in a nutshell, it means I'm going to just allow the action schemas that I have high confidence that are aligned. Okay, I'm gonna put a threshold, and anything that is not aligned, well aligned up to a threshold, I'm not going to consider. So now I have a small subset of well-aligned action schemas. Now they can produce different type of plans because I can solve them in the relaxation actually, and I can actually then solve them and generate plans. I would rank those action schemas by looking at the plans that they generate. And I will select the action schemas that generate plans that rely mostly on actions that have high similarity. Again, and I'm saying a bit too many concepts here, but think about it. I have an action schema with an action A that has 0.9 of similarity, an action B that has a low similarity, and this model relies mostly on action A to generate plans. I would prefer this model. Okay. Now, when we tested it, the off-the-shelf semantic encoder works well, but the type of errors that we have when we translate from PDDL to natural language, they are quite special, and mostly they fall into these categories. You might swap predicates and effects, so that's an error that you might do quite often. You can forget or add a negation. in the wrong place, and you can actually miss some preconditions, or you can add spurious ones. Then you make the problem more constrained or less constrained. So we actually took our problems, we injected errors, and we fine-tuned the model using contrastive learning, which what it means is that if you have negatives, you make sure they're very far away from the positives. Okay? And using this sentence encoder, we have a specialized machine translation, let's say, that look at the similarity, a semantic similarity between PDL, our Russian, with English, which is the natural language description. Now, when we did experiments, we saw that it's enough to have around 10 LLMs. And when I say 10 LLMs, I think that we're trying to turn the problem, which is that probabilistic machines that you poke them once and twice, you get different answer, into our advantage, which means, sure, generate as many interpretations as you want. I will use that, and I will have methods to check their validity. So with 10 LLMs, we managed to generate action schemas up to 6 actions in under 2 minutes. And when we tested the generated plans with human experts that they created different descriptions, they preferred our models better than the ones generated with direct LLMs or with other approaches like tree of thoughts. So this is our contribution in terms of how can we help maybe. So if my thinking is, if in the river crossing, maybe the thinking could have been spent on creating a formal model to get it right. Now, if you want to interact with the tool, Sukai will be on Wednesday in the demo, and now I'll move on to another topic, which also requires modeling, but it's in a different realm. So this is the ARC. The ARC challenge was proposed by Cholet. Cholet is an expert in computer vision that tried to highlight that there is a simple benchmark that he created, ARC, where generalization is challenging and reasoning in abstract, right? It's also, and there is a huge gap between the performance of humans and AI systems. So for those of you that are not familiar, the ARC, here you have 3 examples, 3 grids. You have an input-output, and then you're given a test, and you're asked what is the function that solves the training and the test instance. This puzzle on the left-hand side, you need to detect objects, realize that the coloring aspect changes depending on their size. So if you have objects of size 4, they need to be painted in blue, object size 3 painted in red, and size 2 painted in green. In the middle, you have an object that you need to move 1 step down. And on the right-hand side, you have objects of size 1, that depending on their color, the transformation is different. So you can see that it's quite rich as a domain. There are many types of transformations that you can do. And when researchers looked at how well humans do, they actually do quite well. So 88% of performance. And when we try to look at the AI systems approach, what Cholet suggested is that we can look at it as a problem of program synthesis and using description logics to describe the problem per se. And that's the approach that was followed by the Kaggle competition that won in 2020, and also by the group of Shu and Scott Sanger, that they looked at the approach of creating a domain-specific language and using, I believe it was a constraint solver to find a solution. And the performance, you can see that they only on a subset of problems that focus on object manipulation, they are still far away, okay? Not in the full data set. So with Chao, we try to understand how can we cast this problem as a planning problem. And for us, the most natural way to think about this problem is as generalized planning. So if you're given 3 instances and a test cases, well, this is the classical structure of generalized planning, where you're trying to find a solution concept, which can be expressed as an automaton, or in our case, as a program. So literally program with lines and loops, where that program should be executable and valid for the test cases, training cases, as well as the test cases. So that's how we understand this problem, and we try to encode it using PDL and using solvers in our community. And so Chao proposed the following approach. Okay, so we have first aspect, which is how do you generate the PDL? And you can work at the pixel level. Good luck, okay? But this won't work. So we started looking at what type of abstractions we need to encode in our PDDL domain, such that the mathematical manipulations that we get in our programs, they can be expressed succinctly with few lines of code. And so just to give you a few examples, you need to recognize that pixels, they're not pixels per se, they're objects. So how do you group them together? You can group them using 4 connectedness, or you can use 8 connectedness. Then there are type of transformations. Depending on the properties of the objects, you can think about their shape, you can think about their color. Should you think about manipulations on coloring or movements? And so those considerations are taken when we generate the PDDL description of the task. Once we have the PDDL description, we move into the program synthesis. Now, there's a lot to take in this slide, so don't worry too much about the middle part. Just I think it's interesting to see the right-hand side, the solution concept. It's literally a program that has test. Whenever it says test, it's testing the truth value of a predicate. And if it's false or true, it influences the goto. So it's basically a loop condition. And then there are certain transformations, like extending a node, for us node is an object, into a given direction. Basically, these are pointers, and you're saying extend the direction of this object into wherever is located another object. So we have a set of pointers that we can use to iterate over objects, and we have a given number of program lines, and we needed to introduce the concept of novelty into the world of generalized planning for scalability matters, because even though you can see that the number of lines is not too high, the branching factor is huge, because we need to program the predicates, their arguments were in the lifted level. So this is what a PDDL domain would look like. Something I would like to highlight is that sometimes expressing some updates, it's not trivial in PDDL. So we rely on the concept of external functions, which is something that Guillem introduced in his paper in 2017. So basically, you apply something, and there is a certain recoloring aspect that I could use the right predicates, actions, couldn't be bothered. Let's use external functions because we can express this easily, and we don't need it for reasoning capacities, let's say. So another challenge is that once you have this PDDL domain, the space of program search, let's say, it's still huge. So we started looking at how can we make the program more tractable in the sense that the performance would increase by doing some considerations into which abstractions we will allow in our PDDL. So the first one, it talks about, let's say I have 4 connectedness and 8 connectedness, and then they generate a set of objects, and I realize that the set of objects that both abstractions generate are the same. Well, I should include them both because it just adds symmetry. I don't need it. Action pruning, let's say that in my training instances, all the objects have the same colors, both in the input and the output. Then clearly I should not reason about recoloring. Okay, so I should drop those actions because it will make my life easier. Predicate constraint. So let's say that you need to think about in the conditions, you can use predicates based on properties of the problem. If the property is an invariant, please don't consider it as a condition. That also helps when you're searching for a solution. Argument constraints. If you are going to put arguments within the predicate, make sure that those arguments exist across all training instances, because otherwise it will not generalize. And the last one is that we constrain that whatever we do in terms of transformations always comes at the start of the program, and the rest is just looping through pointers. And we kept that fixed. So that's what encourages is generalization from the following point of view. Whatever transformation we figure out, we make sure that it's reused across several pointers. And this is an example. Of course, the problem of writing in low-level languages, it's hard to interpret, but it can solve this problem. So we have a square that has a perturbation, and the solution is just extend it until the end. And this can be solved with these 4 lines of code, and then just iterations through the pointers, set of pointers that iterate over the objects. And I would say, feel free to check this in your own pace in the paper, but just to show that the sizes of the solutions are quite small. Now, still the challenges exist, and I think there are 2 main challenges. One is that it's not easy to choose which abstraction you should include in your problem. This, I mean, it's a bit of the classical problem in the 70s, expert system. I can always miss some abstraction. So how to do this from first principles, I think it's an open challenge. And another one is, sure, now you've got abstraction, still the problem is hard to solve. So our community is quite trained in creating heuristics. There's a lot of space in creating such guidance. Now, one natural thing to try is, can we try LLMs, for example, to tackle this, because there's a lot of claims that LLMs can solve the RC challenge. Well, so one thing to realize is that they can help us to program. So if we look at the program synthesis, this is the same as the code to text. You're given a natural language description, you have few text examples, and then you ask basically the LLM to generate the code for you. This is basically a program of program synthesis with LLMs. Few of the challenges when you follow this approach is, one, you can get invalid tokens, so wrong, just plainly wrong, but it's easy to detect. Grammatical errors in the language, so it's not conformal with Python, for example, and the ones that are a bit harder to detect, which is the logic is just incorrect. And traditionally in the community, which is quite new, they follow 4 approaches. One is sampling, which is like try again, like a slot machine. It failed, just try again. And of course, criticism is on the right-hand side. That's not very natural for us. Another one is plan. So think before you act, right? So you try to plan and then use that plan to code. The other one is refinement. So you try to, if there is an error, try to refine it through LLMs, just trying to figure out what went wrong. And multi-agent. So you have multiple LLMs trying to coordinate together and come up with a solution. Now, with Chao, again, we published recently this paper where we looked at what we do in planning, which is we actually try to validate. We have a famous val, right, in our community. So the same idea. Before we actually go from planning to coding, generally they would just plan and then throw it to the LLM to code. We said, wait a minute, we can try to validate the plan. Now, interestingly, the validation came from their own LLM. Okay, that's a bit strange, because again, I showed that it cannot check formally that it's correct, but it can actually test with the input tests that there might be some errors. Now, in order to understand the validity of the verification, Chao had the painful task of checking it by hand, and he found that above 90% of the validity was correct. But when the validity was incorrect and you add the LLM to code with that plan, the likelihood of getting a correct code is 0. So if you failed in the planning phase, you will not do well in the coding phase. Okay, and there's quite a few details that Chao tried to introduce here. This is just the result. It's just sort of such a simple idea that even not using our methods, but just our metaphors of how we think about problems, got us into this pretty much the state of the art in coding with LLMs. So that's our approach. So baseline is just direct LLM coding. SP is sampling, so the slot machine. And then you have other approaches that are aligned with what I showed in the previous slide. Human eval is 500 problems, similar to the one that I showed in the opening slide, sorting, for example. And then you increase difficulty by making sure problems have not been seen, so there is no contamination. And then problems that it's not about 20 lines of code, but are actually hard programming tasks. So it requires a bit more. And you can see that in the small problems, actually the performance is quite good, but it degrades, which is expected. So it's still an open problem. And recently, I received this update in my inbox from GitHub saying, look, their agent program mode actually plans now. Okay, and I'm not claiming that they did it because they read our paper, but at least they might be looking at the LLMs and they're seeing the same thing. And so what they say is, look, our plan mode analyzes the text, etc., and before coding, it plans. And I think this is what we try to tell our students as well. Before you code, just think what you're going to code. And so it's not surprising, but ideally we could try to see if we can formalize the verifications step a bit better. So this is just the start, and I think there's plenty of opportunities here. So maybe there is a bit of hope for LLMs to synthesize programs in the RC. Now, in terms of priors, so let's say that now people say that the LLMs have common sense and therefore they have priors that they can use in order to reason in the ARC. So we said, let's try solving the ARC just without us giving them any abstractions. Okay, so let's assume that they have the proper priors, to solve the ARC challenge. If they fail, we give them the ability to reason about objects. So we do our for connectedness and we say, look, when you see these pixels, they're grouped as objects in the following way. If they still fail, we give them priors on geometry, topology, and counting. So they can actually try to reason with these priors. If they still fail, we add goal directedness. Goal directedness is like you're trying to reach an object in a certain location. So we do this type of reasoning ability. And what we saw is the following. So our RSPC stands for repeated sampling planning code, which is you try many times to plan and then code. And then KAR is augmented with abstractions reasoning. And what we realized with GPT-03 Mini, which is the best, let's say, claim to be the best, is that it's still hard. Okay, so first row here is the performance. So the how many problems in the full dataset. So this is the first time that is reported on the full dataset of ARC. How many problems can be solved without any priors? And being a bit clever of how you try to synthesize a solution. You can see that QN you won't solve much, and with O-Mini you will spend a bit of dollars and you will still not solve many. And then if you add priors and objectiveness, the capacity actually improves, which at least tells us that first they don't have that prior embedded, and that is important to reason about objects in the RC. Then we started adding other abstractions, and it did improve, not that much, and it doesn't tell us that they're not needed. It told us that something different, that even if we give them the priors, they don't know how to use it, which is a different challenge. So we tried to understand what are the key aspects that makes it challenging, and of course, one easy thing to look at is the size of the problem. So here you can see 025 means they're grids of size 5 by 5. So whenever the grids of the training cases are 5 by 5, the likelihood of getting a correct answer is quite high. And the shaded part is how much do you win when you give them priors. And so the models that are a bit weaker or smaller, they gain more by having our extra priors. And whenever you start looking at grids of 20 by 20, your chances of getting it right, they're gone. Okay, so size is an issue, scalability. And I think at least here our community have something to say. We know that, for example, the composition is something that we can do, and there are other approaches. So there's a lot of space to make contribution in this space. And then another challenge that we recognize is the ability to read spatial reasoning. So let's say you have to move objects, and you have to extend them, recoloring. So doing transformation over objects, it's not solved at all. So if you have some intuition on how to tackle spatial reasoning, then it's an opportunity to make contribution in this space. So after doing this experiment, so this is something that's a work in progress, so any feedback is welcome. And what we saw is that by adding priors, at least generalization improved. What do I mean? Is that when we got a solution for the training cases, the solution accuracy didn't degrade too much in the test cases, because what happens is that many approaches, they do very well in the training, so they overfit, and then it doesn't work in the test cases. And by adding priors, that gap narrows. But overall, we don't solve many problems. So just to summarize, so opportunities and challenges. So the first challenge that I covered at the start of the talk is that there is ambiguity in human language, and that's inherent in our communication. Sometimes we don't express fully what we intend to say, and one strategy when we communicate with others is that we do some process to make sure that we're aligned. So for example, I try to restate what you said and making sure that you do agree with me. So if you have that problem, our approach at least was using this concept of semantic coherence, so trying to make sure they're in the same semantic embedding space, and using techniques like direct relaxation to make sure that whatever we generate is solvable in the literalized world. Then I think that at least from our community, there's these two challenges, the ARC and coding, that we have a lot to say, and it's like a playing field of opportunities to make contributions. And some of our problems that at least I'm interested to explore next is the following. So I would like the LLMs to generate problems that are easy to solve, okay, that come with guarantees. So why should we ask them to generate PDDL models per se, where I know at least with the ideas of width that I know that if there are certain type of problems that I know that are easy to solve. And so at least I know that I have an easy test on how to test whether the problem complies with that. And I think width is just one example, but there might be many other cases. So whatever you generate, at least make sure that it's solvable easily and it's easy to test. And then one which I'm not sure how to address it is what would be the correct description language to express from first principles the abstractions needed to reason over there, how we learn them. I'll leave it open. Sure. So that's all from me. Thank you.
Thank you so much. Hopefully you are in talks with your lawyer about getting some money out of Microsoft and maybe donating some to ICAPS or no?
Yeah, sure.
Yeah, why not, right? Yeah, thank you so much. So any questions? We have some time. So anybody wants to ask questions?
Maybe to elaborate what you said at the end, okay, so it sounds sense. So one thing is to play the LLM game, okay, so how to align this fist, okay, opaque black box, okay, to whatever you want, okay, and to improve performance, okay, whatever that means or whatever I understand. And the other thing is sort of try to do more principle approximation, so you can elaborate a little bit on these sort of conscious methodological approaches.
Yes. So I mean, at least, so I'll go to this slide. So I'm not sure I found the correct methodology. So far I'm moving more in the space of experimental sciences. Right? I'm trying to understand what happens when you play with it. Now, at least if I can see that if we want them to translate them to formal languages, we need to make sure that we have a method to test whatever validity they generate. So whatever formal language they generate that is valid, and at least that I'm not sure that this is an easy task. So let's say that you want to go from natural language to any type of logic. How can you easily test that the logic is sound, complete, etc.? So one way to do it, at least, is to go into concentrating fragments that are models that are tractable, and planning is not. So then focus on the low at the start of the game. And another way is at least I think work coming up from other labs is trying to add them to formalize the model using coding directly, which is let's forget about the models. We express the transition system with code. That's another method that I've seen, and it's quite successful. But I don't think that I've got it yet. So I don't know if others have ideas.
Any other questions? If not, I had a related question. A few years back at AAAI, I think it was Henry Kotz had this talk about different kinds of neurosymbolic system. So one of the systems is where you have a neural component calling a symbolic component. I feel that's the kind of direction you want to push. Do you see the opposite, where our symbolic planners could leverage domain-specific knowledge that at the level of reasoning, at the time of reasoning, maybe getting partial solutions and stuff like that? Do you see that being an interesting direction to push for?
Yeah, and I think so. The work that come to mind is the work by Augusto, right?
Yes,
that he showed that you can add LLMs to code heuristics, and it can actually work better than domain-independent heuristics. I think yeah. So we are in this round that before, right? The AI was very good at specialized problems. Now is like a jack of all trades. Kind of get it, but doesn't really. So we can use it in our advantage, sure, but it's still very much dependent of the problem. And I think that ARC is a domain where it shows that there is a limit of how far you can go. But yes, absolutely. I mean, it's these methodological aspects that needs to be created.
But why LLMs are not transformers, let's say?
Just because they come pre-trained for you, but it's
But it's trained on the next word prediction, so it's
exactly.
so it's a different thing again than transformers that you can train it for iterative purpose.
Yeah, absolutely. So there's no reason why you wouldn't use transformers. Yeah, and there's other models that may have well defined in this. I think who was Barcelona, right? That proved that said you can show what the expressivity of certain models. That's something actually quite useful. What the expressivity of the models, I'm not sure. But yes, absolutely. Other models are valid as well.
So with the LLMs, the problem is that maybe they are proprietary. We cannot see the data set. We cannot see what procedures are using. For example, ChatGPT, we don't know. It's only the neural model, and there are other aspects that are being using on backbone on the website, and so maybe continue focusing only on the pre-trained parts and be quite challenging to understand this side of the problem.
Okay, so that's a fair comment. Recently, someone here in the it's Ed Hobby. This is a professor in the LLM. He's looking at the problem of can we actually extract the knowledge from property models. So can we actually design the experiment where we can actually look at which neurons are getting triggered depending on which questions you ask, and trying to reverse engineer what are the connections that exist, and you can then uncover biases, etc. So true, it's a challenge, but I think it's also an opportunity because it means that I certainly look at how we can extract that knowledge, understand that knowledge. Yes, John.
Just one thing to add is actually right now you can use the prompt PROB and learn this prompt can tell you in the attention which layer is changed if you inject a new knowledge for your transformer, or it is changed in the attention layer or in the final perception layers. This is one way you can see how you model learn some new knowledge, or does your new knowledge do have the effects to your model.
Any other questions? I do have a few, but maybe I won't bother asking all of them in this phase. But one of the things I do want to understand is, in your opinion, what's the most exciting direction of the space? Maybe something we as a community should be looking at.
Okay. So at least something is getting a lot of traction is the vision reasoning models, right? So it's a vision and language action models. So the application is a robot is looking around the world and trying to come up with actions by having image and multimodality. Now it's exciting because it's an exciting application. It's very direct for us. It's challenging at the same way, right? If it's assuming that we solve the language input, let's add images in them. And so at least the aspect of representation and reasoning with multiple modalities, at least that's an exciting new area that people are looking at planning, but not from our side, from basically robotic side. I think that's an interesting one.
I think at this point, maybe we'll thank Neer again. Thank you so much. Neer is busy running the conference, and it's very kind of him that he took the time to just give us this excellent invited talk. Thank you so much again. Thank you again.
Oops.
Right.